Any questions before we start? So today I would like to cover two topics about perturbations. One, the sudden approximation. And then the adiabatic approximation. Both give us the time evolution of a given system, approximately. Now let's start with the sudden approximation. This is one typical example of this sudden approximation can be, for example, radioactive decay. For example, if you have helium-3 ion, it just has in the nuclei 2 protons, 1 neutron, and then it is ionized, it has 1 electron. Now when it decays through beta decay, it becomes a deuterium. So if you consider the electron in this system, before it was under the influence of the 2 charges at the nucleus. After the decay, suddenly it is under the influence of a single charge. Well, this is an exactly solvable system. This is why this is an example. But even if for the non-ionized helium, you have 2 electrons. 2 electrons initially they are under the influence of a single two positive charges in the nuclei. After this decay, which almost appears suddenly, you have a nuclei which has a single charge. Or a more, let's say, academic example is when you have a particle in a box with one wall that is movable. You suddenly move the box to some other distance. Now, the first is a more real-life example. The second is a more academical example. Now, in both of them, okay, one thing we have to specify is sudden. So let me ask you a question. Is something that happens in 1 millisecond a sudden thing or not?
Depends on the time scale of the system.
Yeah, that's a trick question. It depends on the time scale. So, for example, if you compare it with your watch or what happens in you, well, that's a very short amount of time. But if you compare it, I don't know, the revolution of the electron around the nuclei, it's almost infinitely long. So this sudden is also in that sense, in the sense that in our system, there is a time scale. Let's call that time scale T. The change happens within a time. This is the time scale of the system. The change happens within a time, let's say, tau. Now we are looking at the case when tau over t is much, much less than 1. For example, if you are considering the rotation of Earth around the sun, even a few hours is a very short amount of time. And at the same time, let's write the Schrödinger equation. Now, there are 2 different ways you can look at this problem. One is, let's say, this is the Schrödinger equation. And if we have a time scale capital T, let's say that T is equal to S times T. Then this equation becomes I h bar over T. Now, this is S now. Or I h bar del over del s So this already tells us that in the limit that we can take, you see, t times, t is the, okay. And let's say we have, did I do this right? Yes. So what we have t goes to infinity, right? S is typically of the order of tau. No, sorry. Let me use this one. Because the question, what I am looking at the moment is what happens right after this change. That is what I am interested in. So typically I'm interested in when S is a bit larger than 1. Okay, if this tau times h, for some definition of it, goes to 0, then now, what does it mean tau times h to be 0? Well, you see, h eventually will appear as its matrix elements. Typically, you have, let's say, let me define an omega 1 over t. Omega is a characteristic frequency of my system. Well, the characteristic frequency of my system will be just, for example, the matrix, the E and M are nothing but the matrix elements of H. So if tau times this omega is much, much less than 1, that is, if the time scale is so small, within that time scale, the system doesn't change. That's the basic idea of the sudden approximation. What is this time scale? Well, we said, okay, one definition is energy difference divided by h bar. That's a typical time scale. Or in this case of particle in a box, the time it takes for this particle to go from one wall to the other one, classically, that's a typical time scale. Or if you look at the, I don't know, this decay, the beta decay, the typical time scale will be the revolution of the electron around the nuclei. All these, typically, they all have the same value anyway.
However, for a relativistic particle in a box, would the characteristic time scale be like particle lifetime? Would all changes be measured relative to particle lifetime? Anything we do to a relativistic particle in...
Well, you see, the relativistic particle can have an infinitely long lifetime. You see, the electron can be relativistically moving.
Right.
It has an infinite lifetime.
Particles that decay, I mean, like something
For,
else in the first generation.
okay, for particles that decay, there's another characteristic time scale. The lifetime is a characteristic scale.
Right.
But for example, they can have, take the example of neutron.
Okay.
Neutron in a box.
Right.
Well, it might be that the neutron moves around this box in 1 second, but it lives 15 minutes.
Right.
So the characteristic time scale would be 1 second. Or I don't know, if the box is small, if the neutron moves from one end to the other end in, I don't know, in 1 microsecond, then the characteristic scale will be microsecond.
So,
Anything that happens at a time smaller than that,
so you've got to look at it system by system. There's no.
fixed definition.
Okay.
A system can have many time scales.
Yeah,
You see, look at this electron in the atom. Yes, a one time scale is the energy differences between levels divided by h bar. Another time scale is the rotation time around the nucleus. But these two time scales are more of the same, more or less. But if the system is in a higher orbital, then the energy differences will be very small. So the characteristic time scale for a very excited electron in this system will be very small. So in that case, sudden approximation might not work. So you have to look at it case by case. But then if you establish that the sudden approximation is a good enough approximation for this problem, you basically have an initial value problem. So you have let's say, psi initial. This is before the change happens. Then you have psi, let's say, 0 minus the state just before the change. Then you have psi 0 plus. This is the state just after the change. So here we are assuming that you know how to deal with this change, how the system evolves before the change. We are also assuming that you somehow know how the system evolves after the change. Well, the sudden approximation basically tells us that these two are equal. That is the approximation we are making. During the change, we are saying that the system didn't change. Now let's look at the adiabatic approximation, well, which is somewhat more complicated, but at the same time more interesting. Here we have a Hamiltonian, which depends on certain parameters. And these parameters, they change in time. Now, we still have the time-dependent Schrödinger equation. Well, in a sense, we can still write the time-independent Schrödinger equation. Let me say NT. I'm looking at the eigenstates of the Hamiltonian at the time t. Well, this is like, I have my Hamiltonian, whose parameters are changing with time. For example, it can be, if you consider the particle in a box example, you are slowly changing the size of the box. Or you create a time-dependent magnetic field. The parameter is the magnetic field itself, but this time you are slowly changing the magnetic field with time. So you are slowly rotating it. So this is the system we are looking at. Now, it would have been great if these states also satisfy this equation. But unfortunately, they don't.
The left-hand side is n state as well, right? The state in the left-hand side is also n.
Yes, and right. Now, let's see. But what is the solution of the second equation we wrote? You see, if En of t didn't depend on time t, well, kind of we would say that n of t is equal to n of 0 e to the power minus I over h bar En times t. Well, let's say that we let the system evolve very small steps in time, such that at each step the energy is constant. If we make that approximation, you see what we have is at a given time the energy eigenvalues in quote En of t change with time. They are not constants. But let's imagine that we start from an initial time. We evolve our system one very small time step. That very small time step will have a time dependence given by this equation. Of course, here this will be, let me write it here. I can relate this to the initial value by just summing all these things up. So at every step I'm evolving it by E times delta T, E being the energy of the system at that time. But that sum is nothing but the integral. Well, let me write, this is typically what I would expect. Let me write NT as sum over all states. Cm of possibly t dependence I'm looking for such a solution. I'm sorry, this is 0. In certain limits, this will be the exact solution. That's why I'm basically choosing this form of the solution. And now the question is, what are Cm of t? For example, in the limit that the parameters do not depend on time t, Cm of t will be just a constant. In fact, Cm of t will be just Kronecker data n. Well, let's substitute into our equation. This is the equation we are trying to solve. So
Stating the left-hand side is this time psi, shouldn't be psi, because we are doing linear combinations of all states.
this is my just the last line is just my Schrodinger equation for that this state NT should satisfy.
I'm asking one equation over there.
Here.
T equals A1. Shouldn't the left hand side should be beside because we are summing over all the states?
Well, okay, so that is kind of at t equals 0, I have my state. I have all my eigenstates. I can solve for my eigenstates. If the parameters were not changing, my system will just stay in those eigenstates. Okay. So as time evolves, I am writing the equations. I'm trying to, okay, this is, yes, you're right, sorry. So this is, let me write it in this form if you want. So this is the state that would stay in the eigenstate n if the parameters didn't change.
If R was time independent?
If R, so if R dot is equal to 0, this. So R dot is not strictly the state n. Well, we will show that it actually is state n, but we didn't show it yet. So this is the state which would have been the nth eigenstate of the Hamiltonian if the parameters of the Hamiltonian didn't change. And so this is also our alpha n. Now let's just substitute it into our Schrodinger equation. We would have m, okay, I h bar c m dot is the derivative of c. Then I have the derivative of the exponent. Well, let me. The derivative of the exponent would just give me plus em of t cm times the exponent this is equal to, well, you see, I'm acting h on the state m0, that is just em0. Let me keep it as h. Okay, so this is my equation. Now let me multiply from the left by KT. No, K0. Well, the left-hand side will be I'm making a mistake somewhere. Sorry. Okay, this is the expansion I'm actually making. No. Okay, let's continue. I'm making a mistake. Let me write the t over here and see how it evolves. You see, these states m of t wouldn't evolve if the time were absent. There is a time evolution, their time evolution would be given by that exponent if the parameters didn't change in time. Let's stick with this one. Because
Then
No.
when we say the arbitrary state is a Taylor's
no, that's
it
zero.
should be zero.
Yeah, it should be zero. Well, let's continue. If I make this multiplication, I would have I h bar ck dot plus ek of t ck e to power minus I over h bar from 0 to t e m of t prime dt prime m0. This is equal to m cm of t k h m Well, this is just E m of 0 Kronecker delta mk. So basically I can do the same thing. I can just carry out that summation. This is the part I don't like. I h bar ck dot plus ek ck. There's no m0 here. Times e to power minus I over h bar. This is equal to ck of t ek e to power minus I over h bar em of t prime dt prime. Well, basically this gives me ck that is equal to 0. That's why I think I'm doing a mistake somewhere. So I'm either missing a derivative somewhere, so let's go to this assumption. What am I assuming there? Basically there I am assuming that at t equal to 0, the states m0 are complete. Do they have to be complete?
I think so.
Hmm?
I think so.
So great, so we basically found the eigenstates. These are the eigenstates, right? They shouldn't be. Well, let's check if they are the eigenstates or not. Do they satisfy this equation? Yes, I know the mistake. I know my mistake. Let's look at this one. This is not true. You see, what we know this one. This is how we define them. Now here, this Hamiltonian here is h r of t. But here I have t equal to 0. H r of t m0 is not equal to em of t m0, neither em of 0 m0. That's the mistake I have. So how can we correct it? Let's look at this one. Yeah, okay, we can continue along the same line. But this time, that equation is not the Kronecker delta. Okay, that is something we have to deal with. Now, what is K0? We said that Kt is equal to e to the power minus I over h bar ek of t prime dt prime integral from 0 to t prime. That's how we define it, right? Here. But then this k of k can I say this one? Now, I have a few inconsistencies in my derivation. Okay, where? Let's go back over here. What are the inconsistencies I have? You see, on one hand, this is how I define the state n of t. And then that's also how I define En, the nth energy eigenvalue at the time t. Then I go and say this one, write this equation. This equation does not satisfy that equation over there. So that's kind of the problem I have. And it doesn't have to satisfy that equation. Now what I will do is I will write this equation. With the plus sign in the exponent and m of t on the right-hand side. Why? Let's say what happens if the parameters do not change. Well, if the parameters do not change, that m of t will have e to the power minus I over h bar em of t dependence. The exponent and the time dependence of m of t will cancel each other, so I have the eigenstates, time independent energy eigenstates. So this will just go back to time, well, they are a complete set, and Cm's will just turn out to be Kronecker delta mn e to the power blah blah. So if the parameters do not change, the exponent and m of t, their time dependencies will cancel. I just have the energy eigenstates. That's why I can write it in this form. Now let's see what we have. Just substitute it in our equation. So here this will be a minus sign. There will be an additional term though. There will be the additional term of the derivative of this state. Okay, I will have this equation. Now Hamiltonian acting on this mt will just give me em of t. Oh, let's see. No, let's have the minus. Let's still have the minus sign there. Sorry, I'm constantly changing my mind. Now this term over here, I have h of r of t Let's multiply this with k, t. They are still complete set. So if I multiply on the right with k of t, I would get I h bar ck dot minus ek of t ck. Well, I would rather have a minus sign over there if I want to have the cancellation between. Yeah, I want to have that, sorry. This is minus. This is plus. Okay. So this is em of t. So this term cancels this term. That's the advantage of taking that form for the solution to start with. So what we have is sum over m I h bar cm dot mt plus cm del over del t I h mt e to the power minus I over h bar 0 to t em of t prime dt prime. This is equal to 0. Now let's multiply with k of t. I will get I h bar ck dot k of t e to power minus I over h bar 0 to t e m of t e k of t prime dt prime. This is the first term. Then I will have plus, well, let me also cancel the IH bars. Sum over m c m of t k of t or ck dot kt, this is equal to sum over m cm of t okay, this is the equation we have. For those coefficients, oh sorry, there's no k of t over here. ck dot has this form. Well, still there is that derivative operator over there, which doesn't look nice. Let's get rid of them. So we have this equation. Let's take its time derivative of both sides, and keep in mind that Hamiltonian also depends on time. So the left hand side I have h dot plus h derivative of m of t. This is equal to e m dot of t plus or let me just group them. Or let's you see here I have two terms that have the derivative of m of t. I can group them, and then that would give me h minus e m of t of m of t. This is equal to m of t. Let's multiply it from the left by k of t. That would give me ek of t minus em of t Now, if m is not equal to k, well, basically, if em is not equal to ek, I can divide both sides by ek of t minus em of t, so that gives me kt is equal to minus well, em that doesn't contribute because of the orthogonality of these states. So this is, of course, if m and k are different. Now let's go back to our equation for Cm, Ck. Well, I can write m is equal to k term. Ck dot is equal to Ck of t the exponent is just 0, plus I have a summation over m is not equal to k, C m of t exponent times the matrix element of that derivative, but we had already calculated it. So this is minus, or let me keep it plus, kt h dot mt divided by e m of t minus ek of t. Okay, this is the general solution for our coefficient Ck dot of t. Now you see, if Hamiltonian doesn't change with time, h dot is 0, that is the second term is 0. Mt states are independent of time, the first term is 0, so Ck is 0. So Ck changes with time only if the Hamiltonian is changing with time. Now, the adiabatic approximation is ignoring the second term. You see, if you look at the second term, there we have h dot, the rate of change of Hamiltonian. We are basically saying that if the Hamiltonian is changing very slowly, well, then the question is relative to what? You see, in principle, those differences in the energies can get very small. But that energy difference gives us a characteristic frequency and hence a characteristic time. So if the change in the Hamiltonian within that characteristic time can be neglected, then the second term will be small. You see, the second term can be neglected either that matrix element of the rate of change of Hamiltonian is very small relative to the energy differences. But only for energy differences that contribute to our problem. You say Cm can be 0 for some particular m for which that energy difference is 0. Very small. Then we don't need to worry about that state. Within that approximation, Ck dot will be just kt d over dt mt times Ck, well, which can be solved. Ck of t will be Ck of 0 times the exponent. Sorry, this is k, not m. Because we wrote the m is equal to k term over there as the first term, separated it from the summation, and so there's no m over there. Now Ck of t is whatever value it had initially times the exponent of the integral of that matrix element over time. Okay, so let's look at that matrix element a bit more in detail. You see, one problem I see here is, let's say hypothetically, I don't know what that matrix element is at the time being, but let's say that that matrix element is a negative number, and the integral just grows with t. So then I'm multiplying ck of 0 with the exponent of a negative number that is growing in magnitude with time. But that means I cannot satisfy unitarity.
Not satisfied.
I cannot satisfy unitarity.
Sorry, matrix element is a negative number that's going to infinity.
Yeah, because that exponent goes to 0,
0. Yeah.
so ck of t goes to 0. Or for all k, by the way. And also keep in mind that we said that at t equal to 0, n. So remember, we were looking at this time evolution of this state. At t equal to 0, it's in the nth eigenstate, and we are letting it evolve in time. So this state is what we have found. There's this exponent. Let's go back to our definition of that state. You see, this is how we define the expansion. This is minus. And the n superscript basically told us that at t equal to 0, it was in the nth state. And it would stay in the nth state if the Hamiltonian was not changing in time. You see, that this exponent in the second line, that's just a complex phase. If you take the norm of this state at the time t, that second exponent just doesn't change it. It's just a unitary time evolution. But the first exponent can be problematic if it doesn't have an absolute value of 1. Because that would mean that the probability is not conserved in this approximation. That's not what we want. But we don't really need to worry about that, because keep in mind that kt, this is 1. This is what we want, at least. Let's take the derivative with respect to time. Now we are defining these states kt so that they are unitary and they are normalized to 1 at all times. If you take the time derivative, what you get is d by dt of the bra multiplied by the ket plus the bra multiplied by the derivative of the ket. This is 0. This should be 0. But this is nothing but conjugate. So that tells me that this is such a number that when I add its conjugate to it, I can obtain 0. But that tells me that so this also tells me that this first term is also a unitary time evolution. Another thing that we should note from this expansion is, at least within the adiabatic approximation, we are always in the state n and t. And n and t is the eigenvalue of the Hamiltonian at the time t. It's not the solution of the time-dependent Schrödinger equation on its own, at least not an exact solution. But this solution tells us that it is still an approximate solution of my state if the parameters are changing slowly. Well, what does it mean the parameters are changing slowly? It just means that I can ignore the second term. If I can ignore the second term, then my state, for example, if it started with the ground state, it always remains in the ground state. Or if it started with the first excited state, during this adiabatic change, it always lives in the first excited state. Its state doesn't change. Okay, let's give a break now, if you want. Any questions? Yeah, okay, sorry for the confusion. When I was reviewing, there were a couple of things I didn't pay attention to. Okay, so the question we are having.
So
NT is the eigenvalue of the eigenstate of the Hamiltonian at the time t, meaning at the time t with the parameters the Hamiltonian has at the time t.
So the
So-
second equation in Goldbach says like the eigenstates evolve like this, right?
Yeah, you see, the second equation would say that I would expect the time dependence to be given by that expression. You see, I would expect the eigenstates of the Hamiltonian to be time independent to start with. And I would expect to have only that exponential time dependent state.
Yes.
Then I wrote this expansion saying that, okay, if the Hamiltonian was time independent, there will be an exponential time evolution. It will be just E times T. But now E depends on T. So it shouldn't be just the product of E and T. It should be the integral of the energy. Furthermore, the states and T themselves, since the parameters are changing, the states themselves beyond this exponential will be changing the eigenstates. Plus, well, this product is not the solution of the Schrödinger equation. I should get some corrections in the form of Cm of t to the time evolution. So, for example, if the parameters didn't change,
So is it, this equation is not an arbitrary states equals to linear combination of all the eigenstates at time equals t?
no, this is.
But
But-
if it is, then shouldn't be the state in the right, the same side is n0.
Why?
Because with the exponential it becomes nt then.
Why? You see, nt, well, let me write it in this form.
So I would expect an arbitrary state at time equals t to be a superposition of all the possible states, eigenstates at time equals t.
Well, you can do that also.
There would be say like Cmt times
Mhm.
nt, not exponential. That would be exponential.
You see, the problem is, let's look at this state, nt.
Mhm.
I said that is the eigenvalue of eigenstate of the Hamiltonian.
Okay.
Now let's look at what this is. Now that is if the eigenstate of the Hamiltonian, nt, if it also satisfies this equation. But also the same nt cannot satisfy those two equations. That's kind of the difficulty there. The solution of the first equation is not the solution of the second equation. If it were, let's say it's not, but if it were the solution, well, then I would say that, okay, nt is this one. So the states that I'm looking for, the eigenstates I'm looking for, well, they would evolve because the parameters in the Hamiltonian is changing. So it is this part over here.
Yes.
They will also evolve because they have energy. The energy causes time evolution.
I think I see now.
It is this term over here. But it's not just E times T. That just doesn't make any sense because the evolution will be changing at a different rate at every time.
So we need to take the zero.
So that's why I convert it to an integral rather than just write em of t times t. Then for this combination to be a solution of the time-dependent Schrödinger equation, I'm adding a correction, Cm of t. What is this Cm of t? Well, I don't know. That's what I'm trying to figure out. You see, this state m of t, the only evolution of m of t state is due to the changing of the parameters, not due to the evolution in time. That's the problem. That exponent is, if the parameters were constant, that is the evolution it would have. Plus, this Cm of t is the correction.
Okay, I understand.
And then we said, okay, so we are looking for such a solution. We obtain the coefficients Ck of t satisfy this equation over here, which we wrote as this in the equation in this parenthesis. You see, the second term, in the limit that we can ignore the second term, that's the adiabatic approximation. So Ck of t is, the time derivative of Ck of t is proportional to itself. So if the state started with in the state k, it will remain in the state k. If it started in the state n, it will stay in the state. If it started in the ground state, it will stay in the ground state with the new parameters. It won't leak into other states. It is the second term that causes a particle in a given state to leak into other states. Now, in the next hour, we will look at what happens if the parameters go back to their initial values.
Go back to the initial.
Yeah. And, okay, before looking at that, as an example of an adiabatic change, let's consider Earth. And let's consider a pendulum on Earth. Let's say that this is the pendulum in the equator, going up north and south, north and south. Now, I carry this pendulum to the North Pole. Well, that's an adiabatic chain. Typically, the pendulum will have a very short time compared to the time you take it to the North Pole. It will oscillate back and forth. Now, let's say that I take this pendulum back to the equator, but along this line. It will oscillate east and west. Now let's take this pendulum back to the initial point that I started. Before it oscillated north and south. Now it is oscillating east and west.
So states kind of. So states leaking to each other.
Well, you see, it still has the same energy. It will still have the same energy. So the energy eigenvalue didn't change. Well, this is a classical example. But now here what we see is, well, if the state went back to the initial values, then alpha n of t and n of t, they are the same. They're the same state. They just acquire a phase. Now we will study it next hour. Let's give a break.